Hassium. Hassium is a synthetic chemical element with symbol Hs and atomic number 108. It is named after the German state of Hesse. It is a synthetic element and radioactive. The most stable known isotope, 270Hs, has a half-life of approximately 10 seconds. In the periodic table of the elements, it is a d-block transactinide element. Hassium is a member of the 7th period and belongs to the group 8 elements. It is thus the 6th member of the 6D series of transition metals. Chemistry experiments have confirmed that hassium behaves as the heavier homologue to osmium in group 8. The chemical properties of hassium are characterized only partly, but they compare well with the chemistry of the other group 8 elements. In bulk quantities, hassium is expected to be a silvery metal that reacts readily with oxygen in the air, forming a volatile tetroxide. The synthesis of element 108 was first attempted in 1978 by a research team led by Yuri Oganessian at the Joint Institute for Nuclear Research in Dubna, Moscow Oblast, Russian SFSR, Soviet Union. The team used a reaction that would generate 270,108 from radium and calcium. The researchers were uncertain in interpreting result data. The paper did not unambiguously claim discovery. That same year, another team at JINR investigated the possibility of synthesis of element 108 in reactions between lead and iron. They were uncertain in interpreting result data as well, openly suggesting a possibility that element 108 had not been created. New experiments were performed in 1983. In each experiment, a thin layer of a target material was installed on a rotating wheel and bombarded at a shallow angle. This was made so that fission fragments from spontaneously fissioning nuclides formed could escape the target and be detected in a number of fission track detectors surrounding the wheel. The experiments probably resulted in synthesis of element 108. Bismuth was bombarded with manganese to obtain 263,108, lead was bombarded with iron to obtain 264,108, and californium was bombarded with neon to obtain 270,108. These experiments were not claimed as a discovery and were only announced by Oganessian in a conference rather than in a written report. In 1984, researchers in Dubna published a written report. The researchers performed a number of experiments set up as the previous ones with bombarding target materials with ions of lighter element. Also in 1984, a research team led by Peter Armbruster and Gottfried Munzenberg at the Gesellschaft für Schwerionenforschung in Darmstadt, Hesse, West Germany, attempted to create element 108. The team bombarded a target of lead with accelerated nuclei of iron. They reported synthesis of 3 atoms of 265,108. In 1985, the International Union of Pure and Applied Chemistry and the International Union of Pure and Applied Physics formed a joint working party to assess discoveries and establish final names for the elements with atomic number greater than 100. The party held meetings with delegates from the 3 competing institutes. In 1990, they established criteria on recognition of an element, and in 1991, they finished the work on assessing discoveries, and disbanded. These results were published in 1993. According to the report, the 1984 works from JINR and GSI simultaneously independently established synthesis of element 108. Of the 2 1984 works, the one from GSI was said to be sufficient as a discovery on its own, while the JINR work, which preceded the GSI one, very probably displayed synthesis of element 108, but that is determined in retrospect given the work from Darmstadt. The report concluded that the major credit should be awarded to GSI. According to Mendeleev's nomenclature for unnamed and undiscovered elements, hassium should be known as EKA osmium. In 1979, IUPAC published recommendations according to which the element was to be called uniloctium, a systematic element name as a placeholder, until the element was discovered and a permanent name was decided on. Although widely used in the chemical community on all levels, from chemistry classrooms to advanced textbooks, the recommendations were mostly ignored among scientists in the field, who either called it element 108, with the symbol of E108, or even simply 108, or used the proposed name Hassium. The name Hassium was proposed by Peter Armbruster and his colleagues, the officially recognized German discoverers, in September 1992. It is derived from the Latin name Hesse for the German state of Hesse where the institute is located. In 1994, IUPAC Commission on Nomenclature of Inorganic Chemistry recommended that element 108 be named Hahnium after the German physicist Otto Hahn so that elements named after Hahn and Lise Meitner would be next to each other, honoring their joint discovery of nuclear fission. This was because they felt that Hesse did not merit an element being named after it. GSI protested, saying that this contradicted the long-standing convention to give the discoverer the right to suggest a name. The American Chemical Society supported the GSI. IUPAC relented and the name Hassium was adopted internationally in 1997. Hassium is not known to occur naturally on Earth. The half-lives of all its known isotopes are short enough that no primordial Hassium would have survived to the present day. This does not rule out the possibility of unknown longer-lived isotopes or nuclear isomers existing, some of which could still exist in trace quantities today if they are long-lived enough. In the early 1960s, it was predicted that long-lived deformed isomers of Hassium might occur naturally on Earth in trace quantities. This was theorized in order to explain the extreme radiation damage in some minerals that could not have been caused by any known natural radioisotopes, but could have been caused by super-heavy elements. In 1963, Soviet scientist Viktor Chernentsev, who had previously claimed the existence of primordial curium-247, claimed to have discovered element 108 in natural molybdenite and suggested the name sergenium for it. This name takes its origin in the name for the Silk Road and was explained as coming from Kazakhstan. His rationale for claiming that sergenium was the heavier homologue to osmium was that minerals supposedly containing sergenium formed volatile oxides when boiled in nitric acid, similarly to osmium. His findings were criticized by Soviet physicist Vladimir Kulakov on the grounds that some of the properties Chernentsev claimed sergenium had were inconsistent with the then-current nuclear physics. The chief questions raised by Kulakov were that the claimed alpha decay energy of sergenium was many orders of magnitude lower than expected and the half-life given was 8 orders of magnitude shorter than what would be predicted for a nuclide alpha decaying with the claimed decay energy, but at the same time a corrected half-life in the region of 1016 years would be impossible as it would imply that the samples contained about 100 milligrams of sergenium. In 2003 it was suggested that the observed alpha decay with energy 4.5 MeV could be due to a low energy and strongly enhanced transition between different hyperdeformed states of a Hassium isotope around 271Hs, thus suggesting that the existence of super-heavy elements in nature was at least possible, although unlikely. In 2004, the Joint Institute for Nuclear Research conducted a search for natural Hassium. This was done underground to avoid interference and false positives from cosmic rays, but no results have been released, strongly implying that no natural Hassium was found. The possible extent of primordial Hassium on Earth is uncertain. It might now only exist in traces, or could even have completely decayed by now after having caused the radiation damage long ago. In 2006, it was hypothesized that an isomer of 271Hs might have a half-life of around 7008250000000000000 blackspade times 108 years, which would explain the observation of alpha particles with energies of around 4.4 MeV in some samples of molybdenite and osmiridium. This isomer of 271Hs could be produced from the beta decay of 271BH and 271Sg, which, being homologous to rhenium and molybdenum respectively, should occur in molybdenite along with rhenium and molybdenum if they occurred in nature. Since Hassium is homologous to osmium, it should also occur along with osmium and osmiridium if it occurred in nature. The decay chains of 271BH and 271Sg are very hypothetical and the predicted half-life of this hypothetical Hassium isomer is not long enough for any sufficient quantity to remain on Earth. It is possible that more 271Hs may be deposited on the Earth as the solar system travels through the spiral arms of the Milky Way, which would also explain excesses of plutonium-239 found on the floors of the Pacific Ocean and the Gulf of Finland, but minerals enriched with 271Hs are predicted to also have excesses of uranium-235 and lead-207, and would have different proportions of elements that are formed during spontaneous fission, such as krypton, zirconium, and xenon. Thus, the occurrence of hassium in nature in minerals such as molybdenite and osmoride is theoretically possible, but highly unlikely. A 2007 calculation on the decay properties of unknown neutron-rich isotopes of superheavy elements suggested that the isotope 292Hs may be the most stable superheavy nucleus against alpha decay and spontaneous fission, as a consequence of the shell closure at n equals 184. As such, it was considered as a candidate to exist in nature. However, this nucleus is predicted to be highly unstable toward beta decay, and any beta-stable isotopes of hassium would be too unstable in the other decay channels to possibly be observed in nature. Indeed, a subsequent search for 292Hs in nature along with its congener osmium was unsuccessful, setting an upper limit to its abundance at 3 × 10⁻15 grams of hassium per gram of osmium. Hassium has no stable or naturally occurring isotopes. Several radioactive isotopes have been synthesized in the laboratory, either by fusing two atoms or by observing the decay of heavier elements. 12 different isotopes have been reported with atomic masses from 263 to 277, 3 of which, Hassium-265, Hassium-267, Hassium-269, have known metastable states. Most of these decay predominantly through alpha decay, but some also undergo spontaneous fission. The lightest isotopes, which usually have shorter half-lives, were synthesized by direct fusion between two lighter nuclei and as decay products. The heaviest isotope produced by direct fusion is 271Hs. Heavier isotopes have only been observed as decay products of elements with larger atomic numbers. In 1999, scientists at University of California in Berkeley, California, United States, announced that they had succeeded in synthesizing 3 atoms of 2930G. These parent nuclei were reported to have successively emitted 3 alpha particles to form Hassium-273 nuclei, which were claimed to have undergone an alpha decay, emitting alpha particles with decay energies of 9.78 and 9.47 MeV and half-life 1.2 s, but their claim was retracted in 2001 as it came out the data was fabricated. The isotope was successfully produced in 2010 by the same team. The new data matched the previous data. According to calculations, 108 is a proton magic number for deformed nuclei, and 162 is a neutron magic number for deformed nuclei. This means that such nuclei are permanently deformed in their ground state but have high, narrow fission barriers to further deformation and hence relatively long lifetimes to spontaneous fission. The spontaneous fission half-lives in this region are typically reduced by a factor of 109 in comparison with those in the vicinity of the spherical doubly magic nucleus 298Fl, caused by the narrower fission barrier for such deformed nuclei. Hence, the nucleus 270Hs has promise as a deformed doubly magic nucleus. Experimental data from the decay of the Darmstadtium isotopes 271Ds and 273Ds provides strong evidence for the magic nature of the N equals 162 subshell. The syntheses of 269Hs, 270Hs, and 271Hs also fully support the assignment of N equals 162 as a magic number. In particular, the low decay energy for 270Hs is in complete agreement with calculations. Evidence for the magicity of the Z equals 108 proton shell can be obtained from 2 sources: the variation in the partial spontaneous fission half-lives for isotones and the large gap in the alpha Q value for isotonic nuclei of Hassium and Darmstadtium. For spontaneous fission, it is necessary to measure the half-lives for the isotonic nuclei 268Sg, 270Hs, and 272Ds. Since the isotopes 268Sg and 272Ds are not currently known, and fission of 270Hs has not been measured, this method cannot yet be used to confirm the stabilizing nature of the Z equals 108 shell. Good evidence for the magicity of the Z equals 108 shell can nevertheless be found from the large differences in the alpha decay energies measured for 270Hs, 271Ds, and 273Ds. More conclusive evidence would come from the determination of the decay energy for the unknown nucleus 272Ds. Various calculations show that Hassium should be the heaviest known group 8 element, consistent with the periodic law. Its properties should generally match those expected for a heavier homologue of osmium, with a few deviations arising from relativistic effects. The previous members of group 8 have relatively high melting points. Much like them, Hassium is predicted to be a solid at room temperature, although the melting point of Hassium has not been precisely calculated. Hassium should crystallize in the hexagonal close-packed structure, similarly to its lighter congener osmium. Pure metallic Hassium is calculated to have a bulk modulus comparable to that of diamond. Hassium is expected to have a bulk density of 40.7 g/cm3, the highest of any of the 118 known elements and nearly twice the density of osmium, the most dense measured element, at 22.61 g/cm3. This results from Hassium's high atomic weight, the lanthanide and actinide contractions, and relativistic effects, although production of enough Hassium to measure this quantity would be impractical, and the sample would quickly decay. Osmium is the densest element of the first 6 periods, and its heavier congener Hassium is expected to be the densest element of the first 7 periods. The atomic radius of Hassium is expected to be around 126 pm due to the relativistic stabilization of the 7s orbital and destabilization of the 6d orbital. The Hs end ion is predicted to have an electron configuration of 5f146d57s2, giving up a 6d electron instead of a 7s electron, which is the opposite of the behavior of its lighter homologues. On the other hand, the Hs2+ ion is expected to have an electron configuration of 5f146d57s1, analogous to that calculated for the Os2+ ion. Hassium is the 6th member of the 6d series of transition metals and is expected to be much like the platinum group metals. Calculations on its ionization potentials, atomic radius, as well as radii, orbital energies, and ground levels of its ionized states are similar to that of osmium, implying that Hassium's properties would resemble those of the other group 8 elements, iron, ruthenium, and osmium. Some of these properties were confirmed by gas phase chemistry experiments. The group 8 elements portray a wide variety of oxidation states, but ruthenium and osmium readily portray their group oxidation state of +8, and this state becomes more stable as the group is descended. Thus Hassium is expected to form a stable +8 state. Analogously to its lighter congeners, Hassium is expected to also show other stable lower oxidation states, such as +6, +5, +4, +3, and +2. Indeed, Hassium is expected to be more stable than Hassium in aqueous solution. The group 8 elements show a very distinctive oxide chemistry which allows extrapolations to be made easily for Hassium. All the lighter members have known or hypothetical tetroxides, MO4. Their oxidizing power decreases as one descends the group. FeO4 is not known due to its extraordinarily large electron affinity, which results in the formation of the well-known oxoanion ferrate, FeO2-4. Ruthenium tetroxide, RuO4, formed by oxidation of ruthenium in acid, readily undergoes reduction to ruthenate, RuO2-4. Oxidation of ruthenium metal in air forms the dioxide, RuO2. In contrast, osmium burns to form the stable tetroxide, OSO4, which complexes with the hydroxide ion to form an osmium-8 complex, 2. Therefore, EKA osmium properties for Hassium should be demonstrated by the formation of a stable, very volatile tetroxide HSO4, which undergoes complexation with hydroxide to form a Has8, 2. Ruthenium tetroxide and osmium tetroxide are both volatile, due to their symmetrical tetrahedral molecular geometry and their being charge neutral. Hassium tetroxide should similarly be a very volatile solid. The trend of the volatilities of the group 8 tetroxides is known to be RuO4 OSO4 HSO4, which completely confirms the calculated results. In particular, the calculated enthalpies of adsorption of HSO4, kJ/mol on quartz, agrees very well with the experimental value of 2995540000000000000 black spade 46 plus or minus 2 kJ/mol. Despite the fact that the selection of a volatile Hassium compound for gas phase chemical studies was clear from the beginning, the chemical characterization of Hassium was considered a difficult task for a long time. Although Hassium isotopes were first synthesized in 1984, it was not until 1996 that a Hassium isotope long-lived enough to allow chemical studies to be performed was synthesized. Unfortunately, this Hassium isotope, 269Hs, was then synthesized indirectly from the decay of 277Cn. Not only are indirect synthesis methods not favorable for chemical studies, but also the reaction that produced the isotope 277Cn had a low yield, and thus did not provide enough Hassium atoms for a chemical investigation. The direct synthesis of 269Hs and 270Hs in the reaction 248Cm274XHs appeared more promising, as the cross-section for this reaction was somewhat larger, at 7 pb. This yield was still around 10 times lower than that for the reaction used for the chemical characterization of barium. New techniques for irradiation, separation, and detection had to be introduced before Hassium could be successfully characterized chemically as a typical member of Group 8 in early 2001. Ruthenium and osmium have very similar chemistry due to the lanthanide contraction, but iron shows some differences from them. For example, although ruthenium and osmium form stable tetroxides in which the metal is in the +8 oxidation state, iron does not. Consequently, in preparation for the chemical characterization of Hassium, research is focused on ruthenium and osmium rather than iron, as Hassium was expected to also be similar to ruthenium and osmium due to the actinide contraction. Nevertheless, in the planned experiment to study isocene-2, ferrocene may also be used for comparison along with ruthenocene and osmocene. The first chemistry experiments were performed using gas thermochromatography in 2001, using 172OS and 173OS as a reference. During the experiment, 5 Hassium atoms were synthesized using the reaction 248Cm269Hs. They were then thermalized and oxidized in a mixture of helium and oxygen gas to form the tetroxide. The measured deposition temperature indicated that Hassium oxide is less volatile than osmium tetroxide, OSO4, and places Hassium firmly in group 8. However, the enthalpy of adsorption for HSO4 measured, 2998540000000000000 black spade 46 plus or minus 2 kJ/mol, was significantly lower than what was predicted. 2995633000000000000 black spade 36.7 plus or minus 1.5 kJ/mol, indicating that OSO4 was more volatile than HSO4, contradicting earlier calculations, which implied that they should have very similar volatilities. For comparison, the value for OSO4 is 2995610000000000000 black spade 39 plus or minus 1 kJ/mol. It is possible that Hassium tetroxide interacts differently with the different chemicals used for the detector. Further research is required, including more accurate measurements of the nuclear properties of 269Hs and comparisons with RuO4 in addition to OSO4. In 2004, scientists reacted Hassium tetroxide and sodium hydroxide to form sodium Hassate, a reaction well known with osmium. This was the first acid-base reaction with a Hassium compound, forming sodium Hassate. The team from the University of Mainz were planning to study the electrodeposition of Hassium atoms using the new Tosca facility at the GSI. Their aim was to use the reaction 226Ra270Hs. In addition, scientists at the GSI were hoping to utilize Tosca to study the synthesis and properties of the Hassium compound isocene, HS2, using the reaction 226Ra. This compound is analogous to the lighter ferrocene, ruthenocene, and osmocene, and is expected to have the 2 cyclopentadienyl rings in an eclipsed conformation like ruthenocene and osmocene and not in a staggered conformation like ferrocene. Isocene was chosen because it has Hassium in the low formal oxidation state of +2 rather than the high +8 state which had previously been investigated. and relativistic effects were expected to be stronger in the lower oxidation state. Many metals in the periodic table form metal oceans, so that trends could be more easily determined, and the highly symmetric structure of isotope and its low number of atoms also make relativistic calculations easier. Isotope should be a stable and highly volatile compound.